Hey everyone, and welcome back to the GD&T Master Course. Today, we're diving into Lesson 20 of our Explainer series, and we're tackling a really powerful tool for your engineering toolkit, controlling the entire rotating surface using Total Runout. Whether you're a mechanical designer, a manufacturing engineer, or you're deep in the trenches of CAD and quality control, this is one of those concepts you absolutely have to know inside and out. I'm really excited to get into this with you because honestly, mastering Total Runout is often the deciding factor between a part that just looks pretty on a drawing and a part that actually performs flawlessly out in the real world.
All right, here's a quick roadmap for today's explainer. We'll start with a quick introduction to Total Runout, compare total versus circular runout, dig into the total tolerance zone, look at inspection methods, cover some industry applications, and wrap up with common mistakes and takeaways. We're going to follow a micro to macro arc today, starting with a very tangible shop floor headache, zooming into the mathematical mechanics, and then zooming right back out to the real world.
So let's jump right into Section 1, Introduction to Total Runout. To really appreciate why we even have this specific geometric control, we need to look at a real-world scenario.
Picture this. You've got a freshly manufactured hydraulic piston rod coming off the line. Your inspector checks it using circular runout at a few different cross-sections, maybe one check at the ends and one right in the middle. It passes those checks perfectly. Green lights across the board. But when that rod is actually put into service out in the field, it fails. It leaks, it wears completely unevenly, or maybe it even binds up. So you have to ask yourself, why did it fail if it passed inspection? Well, the answer is simple, but frustrating. The entire rotating surface wasn't uniformly controlled. The spaces between those specific cross-sections you checked had hidden variations, maybe a slight taper or a subtle wave, that a basic circular runout check just wasn't designed to catch.
And that is exactly where Total Runout swoops in to save the day. Total Runout solves this exact blind spot because it's a comprehensive 3D geometric control. Instead of looking at slices, it evaluates the entire rotating surface all at once relative to a specific datum axis. Because it's checking the whole surface simultaneously, it is significantly more restrictive than evaluating isolated cross-sections. You can think of it as the ultimate gatekeeper for rotating features.
Moving on to Section 2, Total versus Circular Runout. To really wrap our heads around this, we need to draw a very hard line between these two callouts, because mixing them up is a classic, expensive mistake.
You probably remember circular runout from our earlier lessons. Think of circular runout as essentially a 2D measurement. It's just measuring the deviation, or the wobble, at individual cross-sections when the part is rotated. It only controls circularity and coaxiality right at those specific slices. Total Runout, on the flip side, takes a full 3D approach. It locks down the entire surface along that datum axis. It checks the whole continuous cylinder, effectively controlling circularity, straightness, taper, and coaxiality all at the exact same time. It's the whole shebang.
Right, on to Section 3, the total tolerance zone. We know what it does practically, but let's look under the hood at the theoretical mechanics of what this tolerance zone is actually doing mathematically.
The big takeaway here is that Total Runout is a composite control. By evaluating the entire length of the feature at once, you're getting an incredible amount of control from just a single callout on your print. If the machinist makes a part with too much taper, it fails Total Runout. If the axis isn't straight, it fails. What if it's perfectly straight but slightly out of round? Fails again. It's guaranteeing overall surface consistency across the board.
So the theoretical mechanism working in the background is that the median points derived from the surface must lie completely within a defined tolerance zone, let's say a tight 0.1 zone. Imagine a strict virtual cylindrical boundary perfectly centered around your datum axis. The entire physical surface of that part has to live inside that invisible cylinder as it rotates a full 360 degrees. If even one tiny microscopic peak or valley breaks that boundary at any point along the shaft, the part is rejected. No exceptions.
Let's transition to Section 4, Inspection and Measurement Methods, because, let's be honest, engineers hate theory without application. Drawing a strict tolerance zone in CAD is easy, but actually proving the part meets it on the shop floor is where things get real.
The traditional physical inspection for this is conceptually straightforward, but it requires serious precision.
First up, you secure the part to the specified datum axis, usually using something like a precision spindle or V-blocks. Second, you rotate the part continuously. Third, and here is the key difference from circular runout. Instead of holding your dial indicator stationary, you actually sweep the indicator longitudinally along the entire continuous surface while the part is spinning. Finally, you measure the total indicator variation, or TIV, the gap between the absolute highest high and the absolute lowest low across that entire swept surface. That is your total runout. Now, obviously, in modern manufacturing environments, we aren't always relying on a machinist meticulously hand-cranking a dial indicator. A lot of this process is heavily automated now. We use coordinate measuring machines, CMMs, and incredibly intelligent model-based metrology software like Verisur, for example. These systems can literally just import the 3D CAD file with all the GD&T data already baked in. The software recognizes these complex simultaneous requirements, figures out the datums, and runs the inspection digitally, which pretty much eliminates those human calculation errors.
Okay, Section 5, Real-World Industry Applications. Since total runout is such an unforgiving, strict control, it is notoriously expensive to manufacture and to inspect. So where is it actually justified? Where do we really use this? Well, you are definitely not going to use this on a standard mounting bolt. You'll see total runout heavily applied in high-stakes, high-precision fields. We're talking aerospace components, bearing assemblies, or that hydraulic piston rod we talked about earlier. Think about a precision spindle or a massive turbine shaft inside industrial rotating machinery. At those extreme high RPMs, even a microscopic uniform surface deviation, or just a tiny bit of taper, can cause catastrophic vibration, tear apart a bearing, or blow a seal. In those cases, total runout is basically your engineering insurance policy. It guarantees those parts spin smoothly and seal perfectly.
All right, final stretch. Section 6, Common Mistakes and Takeaways. Let's talk about the human element here, because GD&T is a language, and like any language, it is incredibly easy to make grammatical errors.
First, a really crucial standard update you need to be aware of. If you follow the ASME Y14-2018 standard, they officially eliminated the concentricity and symmetry symbols. Literally gone. Why? Because they were universally confusing, constantly misapplied, and an absolute nightmare to inspect since they relied on deriving theoretical median points instead of just checking the physical surface. With those old symbols out of the picture, position and runout controls have officially become the definitive, practical options for controlling coaxial features.
So, what are the most common drafting mistakes we actually see out there? Looking at data from engineering forums and metrology experts, the biggest shop floor complaints happen when engineers just overcomplicate things. The absolute biggest sin is slapping a total runout callout on a part where a simple circular runout would have been totally fine, unnecessarily driving up manufacturing costs. Another huge one is anchoring the tolerance to an unstable datum feature or just failing to think about how the supplier will actually measure it. If your machine shop only has basic tools, a hyper-strict total runout callout might just get ignored or verified incorrectly anyway.
I really love this quote from an engineering professional discussing these exact drafting errors. They hit the nail on the head, pointing out that a massive mistake is simply using GD&T for the sake of using it. They remind us that sometimes it's perfectly okay to just use a standard plus or minus callout. You should never, ever use advanced GD&T like total runout just to make your drawing look more sophisticated. Every single callout has to directly serve the functional intent of the part, and you always have to weigh the impact on cost and lead time.
And that brings us to the end of our explainer on total runout. We've covered exactly why it exists, how it differs from circular runout, the nuts and bolts of its 3D tolerance zone, and hopefully how to avoid the trap of over-tolerancing. So I'll leave you with this. Take a look at your current design projects. Are they over-constrained, just burning through your budget, or are they perfectly, practically protected for the real world? Next lesson, Material Condition Modifiers Deep Dive. MMC, LMC, RFS, MMB, LMB, and RMB. We'll see you there.